should we check that screen sharing is working, Jie?
Yes, yes.
Oh, yes, that's a good point.
So Harsh, you just turn on recording, right?
I just turned on recording and I'm making, yeah, now
you
should
disable.
You should be able to share your screen now. Can we just check that?
Okay.
And
Does it work? Yeah.
it's working, yeah. So I think we're all set.
Very good. Well, it's my great pleasure and privilege to introduce Jie Shan, who is a loved and respected member of our own faculty here from 2002 to 2014. She had earned her diploma from Moscow State University in 1996 and her PhD in physics from Columbia University in 2001. And she's now in the School of Applied and Engineering Physics at Cornell University. Her research focuses on the optical and electronic properties of nanoscale materials, and in particular, two-dimensional crystals, such as graphene and the field known as twistonics. Beyond that, she's managed to coax such complicated systems as bilayers of two different materials into yielding new insights into such classic problems as the Hubbard model. And that's what we're going to hear about today. So we're looking forward to that. Jie.
Thank you very much, Phil, for the kind introduction, and Harsh and Shan for the kind invitation. It will always be my pleasure and honor to visit my old home. So this is the view I miss dearly. So this is the window view from Rockefeller 105A. So I have to say, Mike, you are very lucky. Now you have this office. And the other thing I miss is this constant sound of keyboard from my next door neighbor. You all know whom I'm talking about. So today, I would like to share some of the latest stuff. I am very excited myself. But before I do that, I would like to acknowledge my collaborators and my group members. Otherwise, I may forget to do that at the end. So in particular, I would like to thank Professor Kim-Fan Mak, who's been a long-term collaborator, and the group members of our joint group at Cornell. In particular, former postdoc Yang Xu, Yan Hao Tan, and the current members, Ting Xing, Shen Wei, and the two graduate students, Li Zhong and Raymond, we call him, that's Jia Chen. We have been very fortunate to have collaboration with some theorists, including Alan McDonough, Vida Elsa at Cornell, and Liang Fu at MIT. The bulk crystals we got from Columbia, the growth team was led by Jim Hong, and the boron nitride is from National Institute of Material Science of Japan. So with that, so I will give you a little bit of I will remind you about Hubbard model and how we are going to use some material systems to study the model. And then I will tell you a little bit about a few experiments we've been able to do on this two-dimensional semiconductor Moiré superlattices. Okay, so let me just refresh your memory of a Hubbard model a little bit. Okay, so let's consider electrons in this array of atoms, and let's make life simple. We have one non-degeneracy level, and you just have spin up and spin down, double degeneracy. The simplest Hamiltonian to describe a system like this will be just this tight binding model. We have electron that can hop from one side to its neighboring site, described by this hopping parameter T. Right? So the solution of this Hamiltonian is simple. We got bands. Right? As I told you, it has double degeneracy. So if I have 1 electron per site on average, then I should have half filled band. So according to Pauli's principle, so this half filled bands, and this should be a metal, right? And this conclusion should not be dependent on the separation between the atoms. So I always get a metallic behavior if I have 1 electron per site. But of course, we know this is a very simplified picture, and this is not right. And what's missing in this picture is the interaction between electrons. And then the simplest way to include the interaction is just to consider the energy one has to pay by putting the 2 electrons on the same site. So that's the on-site Coulomb repulsion with this energy scale called U. Right? So if you put those 2 terms together, T hopping term and the U interaction term, we got this famous Hubbard model, which was proposed by Hubbard and Gutzwiller and Cornell in the 60s. So the Hubbard model is a very interesting, powerful toy model in condensed matter physics because it is believed, or it is thought, that the Hubbard model can describe a variety of interesting phenomena in condensed matter physics. So for example, superconductivity, quantum magnetism, and can describe a transition from metal to insulator, and so on and so forth. The simplicity of the Hubbard model, when written down, actually is very deceptive. This model can be solved accurately only in 1 dimension. So, we know if you have interaction in 2D and 3D, this becomes very, very complicated. And of course, over the years, the computation side has been making lots of progress. We have many powerful techniques to tackle the problem, but there are always some issues, problems. Therefore, some physical realization of Hubbard model or model Hamiltonian in general in 2D or 3D will be very, very useful to understand what's going on and to solve some long-standing physics problems. And this idea of using some model system to solve, a different quantum problem actually was first proposed by Feynman in the 80s. So what he said, if you can use 1 quantum system to emulate another. So in other words, if you have a very well-controlled quantum system and you can, control the parameters and you can read out the states, then you can use this to understand, what's going on in the different system. And this idea of analog quantum simulator has been well advanced in cold atoms, in optical lattices, or the trapped ions in array. And today, what I'm going to talk about is something sort of a new kid on the block, this Moiré system. So I'm sure you have seen something like this many, many times. We have 1 sheet of graphene, and then if you bring in another sheet and with a little bit twist, then you generate this interference pattern, which we call Moiré, right? So in this particular case, you can see the period is on the order of 10 nanometers. So it's like a 20 or 30 real lattice site. Or you can get the Moiré pattern by putting 2 sheets of slightly different material with a few % of a lattice mismatch, in this case, between those 2 semiconductors. And you also get Moiré pattern, and the period is also on the order of 10 nanometers. So what does this Moiré systems do actually is to introduce new length and energy scale. So I would like to walk you through this very simple, dimensional analysis. So let's consider two energies. One is the interaction energy, and that's inversely proportional to the distance, and this 1 over distance. And the other energy is the bandwidth or kinetic energy of the lowest electronic miniband. Okay. And this bandwidth or kinetic energy is proportional to momentum square, which is 1 over distance square. So if you look at the interaction to bandwidth ratio, it is given by a combination of mass and the separation. So now the Moiré system, I mentioned that you can magnify the real lattice constant from a few angstrom to now 10 nanometer. And if you just put those numbers together, you get this ratio to be bigger or even much bigger than 1. So therefore, by introducing new length scale, we can introduce a strong correlation between the particles. And then of course, I did not consider the depth of the potential. So if you have a deep depth, the particles will be confined more, then this ratio can be even bigger. So now we have such a system, and the power of this Moiré is that you can change the parameters pretty much, at will. So for example, in order to get this phase diagram of high TC, we are changing doping. That means we are growing samples, many, many samples with different doping density, right? And there's a temperature, and then there will be another axis for interaction. So with this Moiré system, you can put the sheets between parallel plates, and that will just serve as a capacitor, right? You can apply voltage across capacitor. That way you can push charge out of system. So you can use gate voltage, use voltage to control the doping density, like average number of electrons per Moiré site continuously. There's also ways to introduce knobs to control this interaction strength. I will talk a little bit about later. And then compared to the atomic simulators, we are dealing with solid state system. So electrons are coupled to phonon bath. You can always cool them down to very low temperature. Low means a small fraction of those characteristic energy scales of your system. So we can study the ground state of the Hamiltonian, which is much harder to do when you have an isolated system like in atomic cases. So the experimental demonstration of Moiré and sort of interesting physical phenomena was highlighted in works from MIT, Pavlo, forgive me, I'm not going to pronounce his last name, from his group. And what I'm showing here is that using the capacitor technique I mentioned, change the gate the voltage, then you can introduce different doping. And for a system near about 1 degree off, you have correlated the insulating state. And then when you dope away from it, and you get the superconductivity. And that was very exciting, a few years ago. So what's going on in this system is that, you can think of those 2 sheets of graphene slightly twisted with respect to each other. So just the low energy physics can be described by those 2 honeycomb, each from 1 layer. The 2 layers hybridize. So if the hybridization energy between the two layers is comparable to kinetic energy, that would change the dispersion of the band. And that happens at a magic angle, which is around 1 degree. So at that particular angle, because the two energy scale becomes comparable, so the linear dispersion now becomes very flat. And this is how we get small bandwidth. And that's the case when interaction becomes important and the correlation comes in. So in twisted bilayer graphene, magic occurs around 1 degree, and you need to be very close to that angle. And also because it's so sensitive to the angle, every device you make will be a little bit different. So the question we ask ourselves is, can we achieve a much wider range of magical angle? Presumably, something like more continuous. Can you achieve more robust correlation physics? And the answer actually is yes. If you consider some material to have band gap to start with, some semiconductor, for example, then you have already kind of isolated band, right? And if now you can introduce periodical potential, either by stacking it to create a Moiré pattern with another material, or externally somehow you can introduce those periodic potential, then we'll have pretty much the same physics, but much simpler, right? Because what you care is to have some kind of periodic potential, and hybridization between the two layers is not required. So this is where we started. So we started with this material called the transition metal that called chalcogenides. And actually, I started this line of work when I was at Case Western. So Lydia, if you look carefully, in the drawer or some cracks in the lab, you may find chips, with the samples on the silicon chips. So anyway, so this is a class material that made of transition metal, either moly or tungsten, and the chalcogenides, silicon, selenium, and they form this structure called trigonoprismatic. So if you look down from top, it just looks like a graphene. So you have metal on the A side, and you have the selenium or sulfur on the other lattice. And the electronic band is very similar at low energy. So sort of like a graphene, but now we have band gap. We have a heavy metal here, so the spin orbit interaction is strong, and that will lift the spin degeneracy of each band. So those bands are spin polarized. But in general, this material it has a time reversal symmetry. So if you go from K point to the K prime or minus K point, spin will also flip. So overall, the band structure looks like this. And it's a semiconductor, so the gap is on the order to 1 to 2 eV. And that's very optics friendly, something that we can probe with photon. So now we introduce this long wavelength period. So in this case, we introduce Moiré potential by stacking it on top of another similar material with slight lattice constant difference. And then you have, this triangular lattice and with period of 8 nanometer. So now if you put electrons, then there will be extra Bragg refraction because of this superlattice period. So then the single band I showed you, for example, at K point, now will be folded, right? And that will give us many mini bands. And there'll always be mechanism, to break the degeneracy here. Now we have an isolated, mini band. And this is the band we are going to study. And this is the band that will, show a lot of strong interaction effects. And this happens, for both electron band and also for hole bands. And we can tune the Fermi energy, as I said, in capacitor by applying gate voltage, tune the Fermi level up and down. Then you can dope the material with a certain number of electrons or holes. And it turns out that this system is very well described by a single band Hubbard model, as shown by Fenchen Wu and Alan McDonald almost 3 years ago. So in this case, the spin degree of freedom is replaced by the valley degree of freedom. So I show you there's a K point and a K prime point, and you can think of those as a pseudo spin. So the parameters have been estimated. So the hopping parameter here is between 1 and 10 millieV, and on-site repulsion is on the order of 100 millieV. So now we have energy scales somewhere intermediate between real solids and atomic in optical lattice system. And one way, another way to think about this problem is that, we have the periodic Moiré potential, and you can load, electrons into those traps, and they form artificial solids, right? And you can think of this like you can do chemistry with those potentials, right? So you can load, one electron and more. And we have actually recently realized a system like this by those two gentlemen here. And what you are looking at here is something we call a penetration capacitance. So you just have two plates, and you have your sample in the middle. If your sample is conducting, it will screen out the field, and then you measure something very low. And if the system in the middle is insulating, then field will have no trouble to penetrate. Then you get a high number. So every time when we load integer number of electrons into those traps, now we have those peaks, insulating states coming out. So we have realized up to 8 elements, so 8 electrons per trap. So the way we make those materials, I would not say too much, just a few words. We use the so-called Scotch tape technique to make those devices. So you come up with a very clean substrate, usually silicon, clean, flat. And you first exfoliate, your bulk crystal. Then there'll be some flakes left on your tape. You put down your tape on your substrate, and by statistics, somewhere you will leave one monolayer or bilayer or trilayer, some thickness flakes behind. But that flake only in touch with silicon substrate and nothing else, right? It's clean. So we can use optical technique to identify which one is one layer. And we can also use optical technique to determine the crystallographic orientation. And then the next step we come in is with a stamp like this. It's made of a polymer, and you can use temperature to control the softness of the polymer. So you can, drop the whole thing or make it sticky to pick up something. Okay. So this polymer has a boron nitride at its bottom. So it's also very clean, the very bottom of it. And this guy will come in, pick up monolayers one by one with very high precision, both in terms of position and angle. And now we're going to have a whole stack of those things. And then you just raise the temperature of your polymer. The whole thing will be just deposited on your substrate. And the polymer can be cleaned out. And this hydronic boron nitride will protect your sample because your sample is not exposed to anything else. So we can get atomically sharp interfaces, very, very low contamination. And then we can, do further lithography. You can put the contacts, you can etch them, and make it into Hubbard, do whatever. Okay, so that's how we make those samples. And then to make a measurement, we can use the optics to probe them, and we can also do transport linear in plane, and we can also measure capacitance I've already described to you. And of course, this is something relatively new. In order to get the certain properties we would like to have, we always have to sort of try to develop or invent new techniques to study something like this, because we are talking about samples of a few atom thick and a few micron in the lateral size. So we're dealing with a very, very small number of electrons or spins, Okay, so with this, I would like to tell you a bit about, a few recent experiments with this kind of platform. What can we study? So the first example I would like to talk about is to look at what happens if you fill 1 electron per trap. And this is the half band filling case. And it's reported in this paper led by this guy, Yan Hao Tan. So first, let's look at the transport result. So this is the resistance of the sample as function of filling factor, how many electrons per Moiré site. So 1 electron per Moiré site, 2 electron per Moiré site, and as function of temperature. And you can see here that we have 2 very pronounced peaks at 1 particle per site and also 2 particles per site. So this is a little bit artificial for very low particle per site. That's because the contact give you a large response. So let's just look at those 2 peaks. So this peak, 2 particles per site, is something we know very well, because now we have completely filled bands, then it's a band insulator. So the resistance will increase when you cool the sample down. So this is just a regular insulator. But the insulating behavior at half filling, 1 particle per site, has a very different nature. This is driven by interaction. When the Coulomb interaction is strong, it can, break this band into 2 by introducing this Coulomb gap. And this state is called Mott insulating state. Right? And that's, of course, only part of the story and a simplified picture. So for Mott insulator, what is important actually is the magnetic interaction. So imagine, if they form this kind of a state, all the charges now are localized. So they ping down at those potential minima, right? And then once you have those localized states, you have also localized the magnetic moment, right? In this case, it would be the pseudo spin. And how the magnetic interact, how they interact magnetically actually determines the nature of the ground state and also the low energy states. So we would like to study the magnetic interaction between those localized moments. And that's kind of the idea we have. And the quantity we would like to measure is something called a magnetic susceptibility. And from a textbook, we know that if you can measure the temperature dependence of a susceptibility, you will get an idea of on the nature of the magnetic interaction. So for example, if the material is paramagnetic, you cool down your sample, your susceptibility diverges at 0 temperature. And if it's ferromagnetic, it diverges at Curie temperature. And if it's antiferromagnetic, you have to extend the high temperature susceptibility, get to a point that looks like it diverges at the negative temperature. So this is like a kind of a simple picture, and it's the Curie-Weiss law, right, describing the interaction of localized moments. And you can also, just look at the 1 over chi and do the linear fit, and that's what experimentalists likes to see, But we have some problem here. As I told you, we have a few atom thick sample and with area size of about micron square. And if you count the number of spins in that system, we have a total about 10,000 spins. And those spins are not isolated. They are embedded in a large background, so any other material can also give you a signal. So in this case, optics comes in very handy. I told you about this semiconductor, right? In this case, because of this valley, we have orbital magnetic moment, and the light couples with this, follows valley-dependent optical selection rules. So if you come in with a left circular polarized light, it will couple only to one valley. And if you come in with a different handedness of light, it will couple to the other valley. So the helicity of photon is a very good probe of the valley pseudospin. Therefore, we can use this technique to look at the difference between K and negative K valley population, sort of speaking. So that's exactly what we did. So we look at the absorption difference between left circular polarized light and the right circular polarized light. If you don't apply any magnetic field, those two valleys are degenerate. So there's no difference between left and right. But now if you apply an outer plane magnetic field, and that magnetic field will generate a Zeeman effect. So one valley will be pushed up, the other one will be pushed down. And then you will see different absorption spectrum for left and the right. So now if you look at either the difference, how much the peak shift, or just to look at the fixed wavelength, how much the difference is, you get a curve like this. And this is, sort of linear when you apply a small magnetic field, and becomes saturated when you apply, above 1 Tesla. So, this actually fits the localize the moment picture nicely, right? If you apply a magnetic field, smaller field, you try to align those localized moments, but then above certain field, all the moments will be aligned by the magnetic field. So to get to magnetic susceptibility, we just need to look at that slope, right? Because this is equivalent to MH, magnetization as function magnetic field curve. So the slope is the susceptibility. So we can get the slope and do 1 over slope, and then as a function of a temperature. And you can see that indeed, at high temperature, it goes linearly. And if you extract this curve, it hits the x-axis at a negative value. And this tells us that the interaction is antiferromagnetic. And this antiferromagnetic interaction between localized moments is very consistent with the Hubbard model when you have strong interaction. So let's just look at those two terms. If U is very big than T, you can treat T as a small perturbation, right? Therefore, it is possible to have, exchange, in this case, a super exchange, for one spin to hop over and hop back. And that's the second order perturbation. But if the two spins on the neighboring site have the same alignment, then this process is forbidden. And only when they are anti-aligned, you get a contribution. And this value, you can estimate it's T squared over U proportional to, and based on all the experimental values we extracted from those measurements, this is fully consistent. And we also know that our system is in the large U over T limit. It's on the order of 20. So I'm not going to get into the details. You can look up those detailed measurement and how we map out the entire phase diagram.
So can I ask a quick clarificatory question?
Sure.
So I noticed that you drive it ferromagnetic. You polarize the spins at about 2 Tesla. And also the parameter theta from the susceptibility is about a degree as well. So those are all consistent with your T squared over U value, is that right?
Exactly, yes.
Okay. Yeah. Okay, great, thanks.
Yeah. Okay, so now I would like to switch gear a little bit and ask a question. What happens if you have, fractional filling? You just put one electron on the average of per 3 sites or 4 sites, So this is the next experiment I would like to introduce. So maybe it's a point to stop, see whether anybody has any question. Okay, sounds like we are okay.
I couldn't unmute fast enough. Just a practical question that goes back. What kind of experimental tolerances do you need in terms of setting up angles? So if, you talked about like a 1 degree angle, and then, I have no feeling for what kind of tolerances you need.
Yeah, so Chuck asked an excellent question about the requirement on the angle, okay? So in the graphene case, I mentioned that it is very critical to get the angle to 1 degree. So the tolerance is very small in that case. But, with this system we are working with, actually, it's much, much better. And the reason is because we have 2 contributions that will give you Moiré. One is due to the lattice mismatch, and that's, in this case, it's a 4%. So for relatively small twist angle, that effect just dominates. So if you are 1 degree off, 5 degree off, it doesn't matter, because that 4% lattice mismatch actually just determines your period. And that's also help us to get sort of homogeneous sample, because the angle disorder is not such a big deal for this. And it's very reproducible. Every device pretty much you see the same behavior.
Okay. Hi, Jie.
Hi.
Can I ask a question since we stopped you anyway?
Yeah.
So you showed these mini bands, right?
Mm-hmm.
And it struck me that you showed them sort of alternatingly concave up and concave down with alternating mass. And that puzzled me, because I would think, okay, I get mini bands in my valence band and I get mini bands in my conduction band, and be sort of separate. So why did they get, positive mass, negative mass, positive mass, negative mass?
I folded them just the way it's, maybe that's not the way you like to draw them. So it's a parabolic band.
It comes from what causes that, if that's really how it is? I was wondering first, is this just the way you draw it, or is it?
This is the way I draw. We can talk a little bit more about this. That's the way I draw them.
Oh, I see. Okay.
Yeah. It's just a band folding, that nothing extra.
Okay. Thank you.
Yeah.
That just puzzled me.
I'm sorry.
Hi, Jie. I have
Hi.
a quick question. Here. So, as compared to the graphene bilayer, the Moiré band in graphene bilayer at metric angle, so these materials like tungsten selenide, they also have very strong spin-up coupling. I was wondering whether these the strong spin-up coupling and the break inversion symmetry, so you have lifted spin degeneracy, will give the Moiré band some non-trivial topological nature.
Yeah, so that's an excellent question. That's something we and others have been searching for. So if you just consider, it turns out the first Moiré mini band is quite isolated from the rest, so it's not topological. However, if you can construct some system like a twisted homobilayer and other ones, it is possible to intertwine, like two different bands. Then you can have band closing, opening. It is possible to get them also topological properties. Nothing has been published yet, but experimentally, but it is possible. And that will make the system much more interesting, at least richer for us to study.
I see, thanks.
How do you control the shift of an angle of 1 degree experimentally?
Easily, Annie. The way we do it, we just use a simple rotation stage. So we first determine which direction is a major axis, and then you come in with rotation stage with micrometer, so you can determine that. So we can routinely achieve something like a ½ degree easily, even with 2 different materials. If you work with the same material, it's easier even. And the way we do it is you have a single crystal, like 1 sheet, and you come in, you pick up half of it, and then not changing anything. And then the other half is left on the plate, right? And you rotate the plate by a certain angle and you put it down. Yeah.
Okay.
Yeah. But the experimental details we need to worry about actually is there are atomic reconstructions, right? So you intend to have twist angle 1 degree, but energetically they may not like that. So that's a separate issue. Okay, so with this, let me switch gear to talk about what's happening at fractional filling. Before I do that, I would like to digress a little bit. I told you, we have to invent experimental techniques on the go, in order to see something like that. And this is the experimental development part. So how do we see states when we have fractional fillings? And remember, those things are buried somewhere, and of course, with a scanning probe, someday you might be able to see, where the electrons are, their energy, this and that. So we sort of developed this optical technique we call the Rydberg sensing technique. And this is also something I started working on when I was still at the case, So imagine that you have a single sheet of semiconductor. Then the Coulomb interaction, in this case, would be electron and a hole generated by optical excitation, will interact very strongly, because you can, naively think about all the electrical field lines responsible for the Coulomb interaction between those 2 particles. They are very much outside your material, so they are not screened too much by anything. So screening is poor for single sheet of material. Therefore, the electron hole interaction is strong, so the binding energy can be as large as ½ eV. And the way you can think about those is just like a two-dimensional hydrogen atom, right? Then we should have those Rydberg states, or those high energy states. So this is schematic, and what I'm showing is optical response as function of energy. Then you have 1s state, 2s, 3s, 4s, till you hit the continuum. That's where band gap is. And something like this, I and the group members at the case at the time, we were able to measure, those absorption spectrum. So the way I would like you to pay attention to is, how they respond to background dielectric material. So if we embed this in some kind of a dielectric background, we expect those binding energy to scale with the dielectric function of the background, right? And in the simple case, it just go as 1 over dielectric constant square, so exact detail may vary depending on how we treat this, but the take-home message is that the binding energy and also the spectral weight are very sensitive to whatever you put around this material. So therefore, the spectrum of those excitons, electron-hole pairs, are very good probe of what's going on nearby. So that's kind of the idea we had. So if you put some kind of a metal next to it, then you expect screening to be strong. Then the binding energy will be smaller, and also this peak will be smaller, right? And if we have a dielectric material nearby, then the screening will be less strong. So binding energy will be big, and the absorption peak will be big. So that's kind of the naive idea we had. So then we did this testing. So we put a single sheet of a semiconductor, a different one, nearby, and then we can dope it using, again, the gate voltage technique. But we only dope the sample, but the probe stays charge neutral. And then you can see what's going on here. It's a 2D sheet. When you dope it, the density function just has a step, right? So this is what we can see in the response of the probe. And this is the 2s state, the 3s state, and 1s is at lower energy, and the intensity is very high. I'm skipping it, okay? So this dashed line divides this, below it, the sample is charge neutral, and above it, this sample is n-doped with electrons. And then you can see that, this 2s state suddenly loses its spectral weight. And also there's a red shift. And this is all consistent with what we understand about the excitons in a single sheet of material. So now we come in with the real experiment. So I have my sample. Now in this case will be this Moiré layers, the electrons sitting in those periodic traps with a period about 10 nanometer. And I will try to load the electrons into those traps, 1 per 3, 1 per 4, whatever. And then I put this sensor layer very close to it, but about 1 nanometer away. So, electrostatically, or I shouldn't say electrostatically, direct electronic interaction between the two is quenched by the spacer layer, because HBN hexagonal boron nitride is very good insulator. But they can still, talk, as what I'm showing schematically here. Okay. And this is what we saw. Okay. So what we are seeing here is just that 2s state, energy of that 2s state as a function of average electron or hole we loaded into the sample. So remember, the sensor is neutral. It doesn't have any doping. So we have a sample layer there, and we keep putting in, on the average of, let's say here, 1 electron per side, 2 electron per side, and on the other side we'll have 1 hole, 2 hole. And the color tells us about the absorption strength, the spectral weight. So you can see here, for example, when the sample is charge neutral, my sensor sees the largest external binding energy and also the largest spectral weight, largest absorption. And now if I come in with 1 electron per Moiré side in my sample, my sensor sees smaller binding energy and also a little bit smaller absorption. Now, if I come in with 2 electrons per Moiré side in my sample, I still see this insulating state. And the same thing happening, if I load holes into the sample. So basically, we have a way to see whether the sample is insulating or it's conducting, right? So every time when you see those blue, large intensity in absorption, that means my sample is insulating. And, so we also saw some fractional filling states, and that tells me my sample is insulating at those fractional states. And in between, we have a conducting sample, conducting material. So how do we understand something like this? So Coulomb interaction by nature is long range. So in addition to on-site Coulomb, the inter-site Coulomb interaction is also important. In particular, when we have our gate, far away from it compared to the period. So in those devices, gate is about 20 nanometer away, and the period is only about 8 nanometer. So the longer range Coulomb, like a neighbor, next neighbor, nearest neighbor interaction can also be important. So we have to consider those extended Coulomb interaction in the Hubbard model. So when we have filling factor smaller than 1, and when V is bigger than T, we can forget about U and T, because in that case, U is just infinity. It tells us you can, very rare, you can put 2 particles at the same site, right? So we can look at this problem sort of classically first. And that's what Walter Elsa did. He did a classical Monte Carlo for this long range interaction, and he has been able to find those configurations, at filling of 1/2, 2/5, 1/3, 1/4, 1/7. At those filling factors, we have this configuration of electrons that give you crystals. Right? So the function of those long-range Coulomb is to minimize V's, right? So the particles, they don't like being at the same site because of U. They also don't like to have close neighbors, just to minimize the long-range Coulomb interaction. And this model actually works very well. It matches all the fractional filling states we've been able to measure experimentally, and also the melting temperature for those crystal states are very well explained, the experimental temperature explained by this model. And what's more interesting is that if you look carefully at some of the patterns, they break rotational symmetry. And in this follow-up work, we look at anisotropy, by measuring optical anisotropy. So the electronic anisotropy has been mapped out spatially for the sample, and we can look at domains, of those states. So anyway, and then you can study even the quantum phase transition of those states. I only want to mention one thing. that this now is a pretty good model system to study different spin Hamiltonians. Now, if you look at different states, they have different symmetry, like linear chain, we have like dimers here, right? And we have, Kagami, at 3/4. So just the different crystal states give you a different symmetry. So I will not say too much more about this. I think my time is running out. I probably should finish. Phil, should I do that?
Well, if it's something fairly brief, you'd like to round off, that would be fine. Otherwise, yes, we have taken our full hour.
Yeah, so, okay. So I'll just skip the last part and I jump to my summary, okay?
Thank you.
So I hope that I have convinced you that the semiconductor Moiré system is a pretty unique, promising platform to study the Hubbard model or some other model Hamiltonian with highly tunable parameters. I've talked about studying the Mott physics, and also, we're going to generalize the Wigner crystal states at the fractional filling. I didn't have time to talk about Mott transition by tuning the interaction at a fixed half band filling. You can find out more in this archive paper. But really, this is just the beginning of it. I am having a lot of fun, and I hope you will find this interesting. And there are many open questions. I listed a few, but the list could be very long. So anyway, with this, I would like to thank for your attention. I'll be happy to answer any questions if you have any more. And I will also be staying, along for some time if anybody would like to have more discussion. You can find my email if you want to have separate discussion. We can also set up, Zoom meeting separately. Thank you.
Well, thank you. That was a really, really fascinating talk. Really appreciated that. You covered a lot of ground, and clearly there was a lot more interesting stuff that we would have loved to have heard, but time being short, we'll hope maybe a return visit at some point. Now I see some hands raised. I guess Walter's already had a question, so let me ask Mohammed for his question. I see Mohammed is unmuted, so. Why don't we move then to Arvind while Mohammed figures what he can do. Arvind, do you have your question?
Oh, hey, thanks for the great talk. This might be something that I'm missing, but I was wondering, like, so you mentioned how you use like the exciton binding basically to sense whether you're in a metallic or insulating state. But like when I looked at the graphs that you showed, it kind of looked like you were still using like the resistivity, the resistance value to like quantify whether you're in, that one. So whether you're in like a metallic or insulating state. I was just wondering what extra information you gained from like the exciton method that you introduced.
Okay. So first of all, this R is reflectance. It's not resistance. So I want to make that clear.
Okay. Yeah, I think that clears it.
So the advantage of, the exciton sensor is maybe a little bit historical, So one side of the story I did not emphasize too much is that we are working with semiconductors, large bandgap semiconductors. So it has been an enormous challenge to be able to have good metal semiconductor contacts. You know, I showed you early results. You know, the contacts are very bad, and after many years of hard work, you know, I think we have figured out how to do this. So in that context, you know, this technique was sort of just developed before we were able to do good transport measurement. So that's first. But, you know, with those small filling factors, transport is still an issue, you know. So if you have large doping density, transport, of course, easier with the contacts. And at higher temperature, everything is easier. So low density, low temperature contacts still an issue. So a technique like this will be very handy. And another way I would like you to think about it is that, you know, now we have this optical technique, right? And you can integrate other ingredients from optics, for example, time resolved measurement. So in principle, you know, you can look at the dynamics, you know, ultrafast dynamics, you know, look at, for example, the dynamic quantum phase transition, all those things now are possible. Did I answer your question?
Yeah, that's very interesting. Thank you.
Okay.
Very good. Mohammed assures me that he's.
Yeah, now it's working. Sorry about that. Thank you so much, Jie, for the talk. Very interesting stuff. I have a couple of quick questions. The first, do you expect something like a charge density wave conductor behavior due to these potentials that are created in the Moore lattice? And the second question, do you see a prospect of using them as spin qubits? Yeah, that's all.
Okay. So regarding charge density waves, right? So if you look at some of those states, depending on, you know, this could be like a range. In the extreme case, you can think of them as Wigner crystal states, generalized the Wigner crystal states, right? If V is much, much bigger than T, but you know, when V and the T gets closer, what T does is for the charge to hop around, right? So if the charge starts to hop around, then the charge distribution will be smeared out a little bit. So you will be transitioning from Wigner crystal state to some kind of a charge density wave. And then eventually, of course, you will quantum melt the whole thing. Yes, so the answer is yes, you know, there is charge density wave states, if that's what you're asking. But
yes, that was.
Yeah. In terms of quantum information science application, it's, well, I think, you know, so this is still on the order of 10 nanometer apart. You know, to control them individually is still, you know, not something, you know, we have the capability. So I think this will be a much longer question and even longer answer. So I'll stop here.
Very
Thanks.
good. We'll turn to Walter.
Yeah, so still about this picture. So they look like candles on a birthday cake to me. And
Yes.
basically, but what strikes me is that on some of them you see two flames on top of each other. So are those just your two Rydberg states of the two different excitons you see?
Okay, so they have different natures. Walter, you have very sharp eyes. So let me just point to some of them, okay? So this is a state when the sample is in its big gap, right? And then, you know, so this is the 2s state, and that's the 3s state. We can still see that. However, for other things, you know, it's a little bit different. So I presented a very simplified picture that, you know, we have some kind of insulating states nearby, and this exciton will see it, right? But maybe a more accurate picture is that I have those states, you know, like the charge pattern like this, right? And I have my single sheet of a semiconductor nearby, and those electrons will impose periodic potential on my single sheet of a semiconductor. And then in that case, that single sheet will have, again, the Moiré effects I talk about. And those actually are the extra Moiré bands contribution coming from them. So you can think of those like those bands now can also fold my exciton dispersion. So I have like this main exciton, and I have the Moiré excitons coming up.
So why do some of these look like parabolas? The blue ones look like they have a dispersion themselves, right?
Yeah. Okay. So that actually tells us a little bit different physics. So let me go back to this. Okay. So maybe this picture is better. So let's just look at what's going on like near this point, when we have a little bit doping, but not too much doping. So now let's think about what's happening. So we have this sample sheet. Now you can think of it as like some kind of a electron gas, right, in the sample. And I have excited electron hole pair here. So the electron hole will interact with the 2D electron gas nearby, and they form, this many body states. Then you can have repulsive and attractive Poron states. And you can see that, so this guy, it's the parabola you were talking about, right? So it's going linearly with density here. And then you have another branch here. So actually one state splits into two branches. One is attractive Poron, the other one is repulsive.
I see. Yeah. So there's much more in this whole picture than you were telling us.
Yes.
Much more information hidden that you can.
So let's move on. This time is moving to Harsh and his question.
Oh, perhaps I'll save mine I have about 50, so I'll save them up for the private discussion.
Very good then.
The question, let's close out with that one.
Okay, let's take Xuan's question, and at that point we'll cease the recording then. Very good.
Yeah.
Xuan.
Great, Jie. It's so great to see you coming back visiting us. Yeah, so I think you skipped like the last part of your talk, but I think I saw some picture maybe showing metal insulator transition.
Yeah, that's something dear to you, right?
Is it like a gate-tuned Mott insulator to metal transition?
Okay, so what we did is a little bit different from what you did. So in your studies, you changed the density, right?
Yeah.
So let me just show this picture. Phil, just give me 1 minute. I'll
Absolutely.
wrap it up.
Several.
Okay. Okay, so this picture probably looks very familiar to you, right? So what we are doing here, we actually fix the filling factor at 1, which is a half filled band, and then we tune the bandwidth, and then you can see, here is the insulating behavior, and here is metallic behavior. And we have seen continuous transition, actually. Oh, we can chat a little bit more about this. We also have a paper on archive. You can.
That's very beautiful. Yeah, very beautiful data.
Yeah, and we followed, the analysis. You guys discussed a long time ago. The quantum critical scaling. Everything works very nicely. They can be rescaled into 2 groups.
Yeah, great. Thank you.
Very good. So we turn to Harsh, who's very good at multitasking, so he can stop the recording and ask his question at the same time, I'm sure. At that point, we'll thank Jie again. Wonderful talk. Wonderful talk. Thank you.
Thank you.
Yeah, thank you. That was a great talk.
Yeah.